Hi everyone, I'm Sara Sarto from the University of Modena Reggio Emilia, and I would like to present to you our work called With a Little Help from Your Own Past, Prototypical Memory Networks for Image Captioning. Image captioning currently relies on transformer-based architecture for extracting the semantics in an image and translating it into linguistically coherent descriptions. Although successful, the attention operator only considers a weighted summation of the projection of the current input. Instead, having access to past training samples at generation time can be a powerful source of information that can increase the description quality. In this paper, we devise a network which can perform attention overactivation obtained while processing other training samples through a prototypical memory model. Our memory models the distribution of past keys and values through the definition of prototypes vectors. Attention layers operate on queries, keys, and values, which are obtained by the same input sequence, if we are talking about self-attention, or a pair of different input sequences, if we're talking about cross-attention. In our case, we are interested in breaking the constraint of operating exclusively on input-dependent data. And so, in memory-augmented attention, this is achieved by extending the set of keys and values to include additional memory vectors. Therefore, the attention operation can employ both input-dependent and memory-specific keys and values. This is the standard captioning architecture. We devise a prototypical memory attention in which we start from the plain query keys and values, but then we extend the keys and values including those of past iterations. Unfortunately, we cannot take simply all the keys and values due to memory and computational problems. Therefore, at each iteration, we store the keys and values up to a certain defined limit number. And then, we cluster the manifold identified by the memory bank of keys and values, and we take the resulting centroids. Those centroids will be concatenated to the current keys and used as prototypical memory. For the value side, we obtain the augmentation by interpolating the values corresponding to the keys that lies in each cluster, and the function top k returns the closest key value pairs in the memory bank. Placing all keys and values produced during an entire Cocoa epoch will require storing around 96 million memory vectors, and this will make the problem intractable in terms of memory occupation and computational complexity. Therefore, we build synthetic key-value pairs as prototypical memory vectors, which are representative of the distribution of the entire memory bank. Moreover, building prototypes should be fast, and also memory prototypes should evolve continuously to adapt to the changing distribution of keys and values. To ensure a continuous update of the memories, we adopt a strided sliding window approach to update the memory banks. Therefore, at regular intervals, we take the last t batches from the key value stream, we create a memory bank with those, and finally, we generate prototype vectors. All this process is repeated frequently. In this slide, we report the results on the Cocoa test server, in which we can see that our model surpasses the compare approaches by a large margin, demonstrating its effectiveness on the Cocoa dataset. Here, instead, we show some qualitative results in which our model demonstrates a better generation quality than a transformer that does not make use of the prototypical memories. Thanks for your attention.